Alright, so for this homework we're going to look at fitting non-dimensionalized data. In this case we're going to make some synthetic data with relative error for the Nusselt number, and then we're going to plot that, generate an equation, and show a line of best fit. We're going to do that using Python. So first things first, we'll go ahead and import all of our packages in. So I'm just importing NumPy and our subplots so we can eventually graph our data and some additional things for our plots. And then from SciPy, importing the minimize function so we can ultimately minimize our relative square error for our synthetic data. So the first thing that we're going to do is we'll go ahead and define our variables that were given in the problem. So in this problem we were given C1, C2, C3, A, B, C, and D. So we'll go ahead and put all of those values in. So what the first part of the question is asking us, for Reynolds numbers logarithmically spaced equally from 10 to the negative 4th, 10 to the 10th, and Prandtl numbers logarithmically spaced equally from 10 to the negative 1st to 10 to the 4th, randomly choose 50 pairs of Reynolds and Prandtl numbers, calculate the Nusselt number using the equation parameters above. So again, we just put in all of our variables here, and we're going to ultimately be putting them into this equation to solve for our Nusselt number. So to equally space our Reynolds and Prandtl number and then randomly choose 50 pairs, this is what we're going to do. So we're first going to make a range for our random values. So we'll do np random dot random state, and that's, I'll just put in 1, 1, 1, 1, 1, something. This basically just gives us a code so we are always generating the same random data. And then for our Reynolds number, we're going to make sure that our logarithmic spacings are within that random range associated to our random state code. So we'll use np log space. So to logarithmically space them from negative 4, 10 to the negative 4 to 10 to the 10th, and we'll do that to n values. Oops, I gotta put that in too. So n we'll say is equal to 50 since we want 50 pairs. So we essentially just want 50 values for both the Prandtl and the Reynolds number. And then for our Prandtl number, we will do essentially the same thing that we just did for the Reynolds number, except we'll go from 10 to the negative 1 to 10 to the 4th. And then that'll be also 2 increment of n. Okay, so now we'll plug in all of our values into our Nusselt number equation. So we'll do oops. Oh, don't want that. So this would generate our vector for our baseline synthetic data for our Nusselt number. But what this is also asking us to do is, now that we have the synthetic data, we want to basically simulate a constant relative error of 2%. So we're going to use an average of 1 and a standard deviation of 0.02 to do that. So we'll essentially just be multiplying our Nusselt number by a vector of the same size that has randomly distributed values with an average of 1 and a standard deviation of 0.02. So we'll make a new variable, we'll call that new data is equal to our Nusselt number that we just calculated times MP random dot normal. Oops. And this will give us a normal distribution around 1. Again, our standard deviation is 0.02. And then our size of our vector, again, will be equal to n, so it stays consistent. And then we need some x values for when we're plotting this. So I'll just do x equals np dot length space from 1 to 50 with an increment of n. I'll actually go ahead and I'll print the Nusselt number data. So this is what our Nusselt number data looks like right now. So next thing we're going to do is generate our coefficients for our line of best fit equation that will show up on our plot. So easiest thing for us to do is we'll first try doing a linear fit to this data. So we'll use NP polyfit for that. And we are using our values from our x vector and our values from our Nusselt number data vector. And this will give us our values for m, our slope, and b, our y-intercept. So we'll do our y-fit, or like our line of best fit, is then equal to our value for m times x plus b. And then, oops. And then I'll go ahead and print our value for m. I'll print our value for b, so that we can see those. Oops. Oh. What did I do? Oh. Oops. Polyfit. So these are coefficients for our m and our b in our linear fit here. So then next thing we'll do is we'll go ahead and actually make our plots. So now we'll go ahead and run all this. Where did that go? Oh. Oops. There it goes. Alright. So that's our Nusselt number data. Now the next thing that we have to do is minimize the mean relative square error between the model and the synthetic data. So go ahead and do that. So first off, start off by defining square error. We'll do that at v. So we'll initially start off by saying that v, that our a, b, c, d, c1, c2, and c3 equal our b. Oops. And that our Nusselt number model will equal, again, our equation from up here. I'm just going to copy and paste that. And then we'll do the mean. We'll return the mean value between our model and our synthetic data. And we'll square that since we're looking for the relative square error. So now we want to go ahead and minimize our square error. So we need to first give a guess. So we'll just do our first guess based off the values that were given in the problem. So A, B, C, D, C1, C2, and C3. And then our result will minimize our defined square error function in relation to our initial guess. And I'll print our result to show, based on this data and our line of best fit, what essentially like our R squared value is. So that's what we get when we minimize. And again, our corresponding coefficients for our best fit line are shown here, with our slope being about 0.3645 and our y-intercept being 22.3629 based off of this random data.